Okay, well, welcome to our April community meeting for Pravega. I've got a quick introduction here, and then we'll get into talks. Our last call was March 12th. We tried out Bevy. It worked okay, but we're back on Zoom. The talks are on the Pravega IO YouTube channel. We got about 4 times as much viewership on YouTube than we did in the live session. That was kind of something I was hoping for. And I split out the technical talks. So consumption-based retention, schema registry, and SLTS are up there as individual talks. Share those out, with colleagues as you encounter people who are interested in these subjects, or by all means, give them to your grandma, those who spoke. And then this URL, community.cnc/Pravega-community, that's where you can, I guess, see the schedule for these things and get the slides and videos for the prior sessions. So this will be up there today, but these are things we can start sharing out. I think it's important that we, not only advertise what semantics we achieve, but how we achieve them, to grow mind share for Pravega. Certainly doing things in unique ways. So it's important that our colleagues in the computing world kind of understand what we're up to. I just wanted to highlight a few community developments since we last met. We had an improved build and test environment. Many flaky or sporadic tests were fixed. Build times have improved. Fewer repeating of the build due to failed tests. This is kind of a beneficial result of some tech debt sprints that we did at Dell. We also have improved documentation. We're publishing docs at a new place, pravega.io/docs/nightly. So merges to master can get published to this nightly folder. We have our improved docs will, I guess, maybe come out in the 010 release. So they're in the nightly folder currently. We have an improved website at pravega.io. We recently completed that. And the Pravega Hackathon marketing and registration are underway at unboundedhackathon.com. That's in partnership with Dell Technologies and Angel Hack.
You shouldn't mention the price, Derek.
I will. I have a slide on it. So I just want to show this. There's a screenshot of the new docs. We have a new kind of information architecture here under the nav menu. You can see we have a more getting started guides to kind of get different people interested in what we can do. We've reorganized and provided more information about connectors and the ecosystem and tools. And we're highlighting docs from other repositories, such as the schema registry. And we've got this new admin guide that pulls in, some of these are new docs in the Pravega repo and docs coming out of the operators repository. So, and it was really cool to see, the SDP product be able to leverage these documentations in the same way. So I think we're getting some good synergy, and improvements will keep coming. I think, docs for consumption-based retention are pending, and we'll be landing maybe in 010 as well. So we'll have more improvements here. This is just a screenshot of the new website. One of the docs got a video in conjunction with the hackathon. So that was, I think this is an improvement. And of course, the Pravega Hackathon, it's called Unbounded. It's at unboundedhackathon.com. There's a $5,000 grand prize. The challenge is basically, this is kind of the official text of the challenge. Think of a creative idea. What is a problem or a pain point that can be solved using real-time data analysis? Find some real examples of that data or create your own. Use that stream of data in pravega.io to create code to create an analysis necessary for your idea to work. For your submission, you will need to write a document, a PDF, create a video using Zoom to discuss your idea, and submit your GitHub project. This hackathon is open to 18 years or older and legal residents of the United States, Asia Pacific, and Japan only. So I think India and China are in Asia Pacific. I'm not sure all the countries, but it's pretty broad. The people there know they're in it. Also, the 010 release cycle is ramping up. This is just a highlight of what may be in the roadmap for 010. Discussions have started. So video analytics, security, serviceability, performance, operator scaling, key value store beta 2, which we'll hear about today, and then consumption-based retention as production ready. Of course, more things will land, bug fixes and all kinds of stuff. I may push a few of my pet concerns in. We'll see, but join that discussion. Our next call will be May 21st. We're going to try maybe a later time for the US audience. Maybe 11 a.m., maybe noon. We'll maybe nail down the exact time, but May 21st, the hackathon's on the 14th. So basically I have to do the 21st in May. And the topic will be connectors. We'll do the Flink connector, the GStreamer plugins, and the Presto connector. Yeah.
So I don't think we have a channel or anything in our public like to talk about 010 features and such, right? So you talk about, let's discuss it, but yeah. So let's open this up so that we can get input from others as well.
Yeah. So we'll create a forum for that discussion as well. And today's call, our agenda is we'll actually do a different order than this. Akka connector will go first. Olivier needs to head home soon. Then we'll do the key value tables and the performance evaluation. So without further ado, if you're ready, Olivier, I'll stop sharing and you can, how do I stop sharing? Oh, there it is.
Should see my screen. Okay. Okay, nice to meet you. I'm Olivier. As my little French accent should denote, I live in France, and I've started to play, to be honest, with Pravega 2 years ago. I discovered it through a Flink presentation, and I wanted to try to make some connector for Alpakka, which is Akka Stream community project. So we will show you some advances on this topic. This is the fast agenda. I just take the time. I will quickly present Akka Stream, Alpakka, and a little part of the general Akka Stream API, and of course the Pravega connector, and a small demo, and perhaps we can talk a little bit about what we could do tomorrow. First of all, Akka. What is Akka? Akka is a main actor library of the Scala ecosystem, and also Java, of course. And to be very simple explanation, Akka are just actor are just objects that are part of a hierarchy with a notion of supervision. That means that an actor has a parent and child relationship, which means that the life cycle of the children are handled by the parent. It can cover the error cases, or also creation and deletion. Actors are communicating only by message passing. So there is notion of mailbox tied to each actor, and that's it for the actor. It's a quite common pattern. I think everybody has heard about it. Akka Stream is a streaming library built on Akka. It provides type-safe streaming. Of course, I will explain what is it. To be, it's the Akka Stream defined, not of course every streaming API defines this concept. Some of the building blocks, source, things, flows, and many others. They are highly composable in a sense, as you can. Do you see my mouse pointer? I don't know.
Yeah, we can see that well.
You can see it moving. Okay, so you can group together a source with a flow and with another flow and building a composite source like this, or many other composition, of course. And Akka Stream main benefit is to provide back pressure for free. You see, it's quite simple to use. And when I say highly composable, okay, you can also compose the composition, of course, and this is recursive and has no real limit. So the end, you obtain you have to provide a runnable graph, which is a closed shape, okay, which can have a source and an end. Alpakka is the project. It's an open stream initiative, sorry, an open source initiative, which provide many patterns of streaming, some transformation utilities, and of course some connectors. There are now about 20 or 30 connectors. It's intended to be the camel of Akka Stream. I think that everybody knows about camel, and of course the Pravega connector. So, from my point of view, what is this connector? It's just a source that consume that can consume on the topic stream from Pravega, or a flow that can write to Pravega or read from Pravega. So, just to illustrate the composition of the library, when we want to provide a stream, not a stream, a sync from a flow, it's very easy. You have a flow, you added a sync which ignore the input, and then from a flow you build a sync. As a very simple example, I will show you how to implement a source, a number source, which obviously is a source that provides integers from 1 to overflow. It's I don't go. First of all, it's a real code. Okay, it's not a simplification. So this is the whole code you have to provide to make a source. So it's a source. Why it's a source? Because it has a shape of source that produces int. Everything is typed. There is the notion of outlet, okay, because a source has an output, and there's many other details, and the implementation goes in this function. This function is just there, and it's nothing more than having an initial value and react every time somebody asks you for a new value. You push the value and increment the counter, and that's all you have to do to make a source component. Of course, and then Pravega is no more than using the Pravega API to provide provide a source and a flow. So I will show you a very simple usage of the API. That's a sync, so a way to write into Pravega. Okay, that's just a thing. So we can go. I don't know too much time. So we can go very simply into the API. A sync is with this function. We provide a sync from a scope and a stream name via a flow. That's what the simple I was giving. I gave a few minutes ago. A flow that we ignore the output. So the flow, you can see the same code as the int generator. Of course, the logic of producing the result is quite different. It uses the API of Pravega and some semaphores to handle the velocity of the connector. So I close this, and this simple usage is there. Okay, I will generate a sequence of number from 1 to 10 in this example, provide the string, and write the string in the sync. So if everything works smoothly, so I didn't start my shells. You see the shell? Hello?
Yeah, we see your terminals.
Is it big enough?
Yeah, building SPT in both. Yep.
Yeah. Okay. So in this very, when I run for the demo, the writer, which is this code, okay, sorry. It's just read, it will print out the names from 1 to 10, and the data are put in Pravega. So if I build, yes. So then there is a topic, not a topic, a stream with 10 values. So in the same way, you have to write a reader from a reader group. That's where I understand very recently how we're working reader groups. And this is as simple. From a reader group, you read a source, which will be, sorry, a source of string. You can see in the type, which is a source of Pravega event containing strings. And of course, if I hopefully run the reader, a good one, this one, it will read the 10 events, and I can, of course, provide more events. They will be read again. Okay. Close. So this simple demonstration of how to write and to read from Pravega. Of course, there are many more usage than using pure string. And just to play a little bit, with Akka Stream API, I implement this workflow. Okay. This time we have two streams, A and B. So two sources, a merge component that merges the result of the two topics. After that, I broadcast in two pipes. One pipe that do nothing, the other pipes that will make a lookup in a Akka VP table to retrieve a value if it exists, and zip the result of the two substream in a tuple. So key-value pair, string and the count, and update the count in the KeyValue table after that. Okay, so here I have a name 1, name 2, the input I showed you just before. In broadcast names for every record, of course, they will be broadcast on the two pipes. Name 1 and return the count there, and after I increment the count in the table. And that I will show you how to implement this in Akka Stream. As we will see, it's very funny. I find this very funny. And the end result is a stream of tuple, name a string to int. Is it clear?
Yeah, yeah, it is for me.
And if you want to, this is in ASCII art. You may think the representation of this workflow. In fact, not. It's not an ASCII art. It's real code. It's real implementation. As you can see, there is a quite perfect match with the drawing and the code. Okay, I have sources, merge component.
Olivier.
Sorry.
Hey, just one quick question. So this lookup component here,
I will
so
show you.
this is an operator.
No,
So
I will show you just
Pravega symbol is. Okay.
2 minutes.
I'll hold on to my question then.
That's no problem. So as you can see, it's there is a good match from the specification and the code. I show you the code that isn't for that. This is what the PAP. Okay, you can see the screenshot I took for to implement and to make the slide, in fact. And your question is there. Lookup. It's a flow. I've made some helper method, of course, because it's not very funny. It's just a Pravega table with flow to a scope, table and family extractor. It's the API of KeyValue Table, I think, and I will explain more how it works. And first, you declare all your components independently, and then you attach input and output of inlet and outlet of each component to produce source. Okay, so this is a composite source that will produce tuples from the string and the count of the string in the Pravega table. Okay, that's it. Lookup. The lookup will just make a lookup in the table. If there is no entry, I say it's the first one I encounter this entry, or else I increment the count. And after I update, same way. Read through. It's very every time the same thing. In fact, read through, and that produces that receive a tuple and let it pass downstream. And if it won't work, it will be nice. So I have to run this reader. This is waiting. I think, and I send here 5 messages in B-stream. They arrive there. Up again, 5 messages in A-stream. And it stops because I wanted just to listen to wait for 10 messages, 10 tuples. And of course, if I run again, this time I send 10 messages, so there will be sent to up 1 to 10, not 1 to 5, and up. There's a new count. I already consumed 10 messages. Okay, so. And of course, they arrive in certain order. The value after 5 are just 1, and that's it for the small demonstration of how work this API of graph of those implementation. In near future, I need to stabilize and clean up what I've learned from Pravega API, because at some point I done some mistake, mainly because I knew Kafka and I thought it was the same kind of API. I need to see how to implement something with transaction checkpoint, as it's quite complicated, in fact, because streaming and transactions are not so easy to implement. And I will probably do the same things that Think with the checkpointing. I'd like to know also what to do with the property of Pravega to dynamically scale the partitions. If I can use this in Akka Stream with some substrings temporary, I don't know. And of course, I'll provide an API because for the moment it's quite raw. And that's it for me. Do you have some questions or remarks?
You kind
I
of
do
blew my
have-
mind that ASCII art was executable.
Excuse me. Yeah, I can see you. Where is the screen? I lost the image. Again. You said? Sorry. I didn't get you.
Oh, I just said I was really surprised that the ASCII art was actually executable.
Yeah, that's nice. It's because of Scala, because Scala has the ability to redefine operators, and it's just method calls, in fact. Okay, and with infix syntax. So when you see what is very handy to use, that this, if you see the overline, it's a source, okay, of the string. I have two source of strings that I merge in a fan from two string from one string. After it's a fan, it's a broadcast operator and things like that. Okay, it's a flow to int. Okay, because I ask to the KVP table the value, the int value from the and also and zip component also, which sorry, it's takes a stream of int and a string and produces a stream of tuple, and this one the shape the component will write back to KVP table. In fact, it's just they are just objects. Okay, there. And the method exists. Sorry, you can see I should I don't know, my editor is not, but it's just a method call, in fact, with the infix syntax. But that's quite. Of course, when you write in Java, you cannot use this syntax. It's clearly more verbose, but it's okay also. The connector is you can use this connector with a Scala API or Java APIs, of course. It's mandatory for Alpakka. That's it.
Hey, Olivier, I have a couple of questions. Can you go back to your last slide?
Of course. Last one.
Yeah. So a couple of quick questions. Yeah, exactly. So that one. Yeah, this one. So when you talked about transactions, you said that this is quite complicated. So I assume you're saying this is complicated on the Akka side. So what is the complication you're referring to? I'm just curious about that.
And, okay, for me, just complicated to know where to start the transaction, where to end the transaction, because streaming is infinite. So what is the logic? Where can I start end the transaction? I have no idea of how to implement this, in fact.
So Akka has no notion of say checkpoints or snapshots or anything?
No.
Akka doesn't have that notion?
No, as far as I know. It's not it's just a planning API. Okay, you have to implement your own logic.
Okay, so that was one question.
I don't know.
Second one
I know
is for the third bullet, scale with
some
dynamic
discussion
string
about
partition.
this.
Does Akka have any mechanism for scaling a workflow?
Some tooling. My connection is unstable.
It sounded like he wasn't able to hear you.
Did you? Okay, so let me repeat the question.
Sorry.
So for the third bullet, scale with dynamic string partition, I am one. So I was thinking when you mentioned that, I was thinking about how to do it. And my first question is, or my question is, does Akka provide any mechanism for scaling a workflow?
Yes. Yes, yes. There are many. You can change the parallelisms of operators. Okay. So I imagine I can listen to. I have some mechanism to listen to Pravega partition scaling and react on my part to multiple the parallelism.
Yeah, this sounds like a great one to follow up. I mean, this is great. We should discuss this more offline.
Exactly.
Oh, thanks.
Thank you. And there is also a component, two components that are merge hub and the other part, the broadcast hub, which has some kind of hub. You can add some pipes dynamically. Okay, you can you at runtime you instantiate a graph and you attach it to the hub. And I'd like to talk about this. Okay.
Yeah, let's do that. I think it's a great topic to follow up.
Thank you.
Yeah, the mailboxes in Akka are basically in-memory queues. They call them mailboxes. Any other questions? That was really great, Olivier. It was cool to see key-value tables in action so simply.
Thank you for the demo.
Yeah.
Thank you for Pravega.
Yeah, you're welcome. Let's see, I guess, are we ready to go on key-value tables, Andre?
Yes, I am.
All right.
As I can find my Windows, 1 second. All right, I'm finally doing this. So, hey everyone, so next 20-25 minutes, I'm gonna be talking about key-value tables, which is to Pravega since 0.8. We've added this thing as a top-level primitive sibling to streams. And in our view, this is a perfect complement to our streaming workloads. And in this presentation, I'm going to show you why we think it's like that, and also what changes are coming down the pipeline in the upcoming 0.10 release, and what should you expect in the future from us. All right. All right, so first of all, what are key-value tables? It's literally a distributed key-value store. They are backed by what we call table segments. A table segment are key-value stores on top of regular Pravega segments, which are the same segments that we use for streaming. It's the same technology used to maintain all of the Pravega metadata. So since version 0.6, all of our scopes, streams, segments, transactions, and now in 0.9 SLTS chunks and everything else you call metadata in Pravega is stored within our cells via table segments. So what are these table segments? So table segments are pretty much like a hash table abstraction on top of Pravega segments. So you can do anything. You can insert keys, you can look up keys, you can retrieve, of course, otherwise it will not be very useful. And you can also list keys. So in a nutshell, if I can summarize how they work, all of the updates for table segments, they are appended to the backing segment, which is used as a changelog. The keys are hashed to 16 bytes, and then those hashes are stored in our segment attributes. Segment attributes were introduced a while back to support our exactly one semantics. For streaming workloads, we use them to maintain the writer states, but we have since expanded them to be able to support other types of metadata, and currently they are implemented as a B+ tree on top of tier 2 with various levels of caching. So they're also used for other types of metadata, but essentially we can store tens of millions of tiny pieces of information in this thing, which is why we found them as an excellent storage for our table segment index. All right, so a quick summary of the features supported by key-value tables. So you can do anything you expect with a hash table. You can do single key insertions, updates, and removals, and they can be conditional or unconditional. What does conditional mean in this case? Every time you insert or update a key, it gets some sort of a server-assigned version, which you can view as an e-tag. And you get that thing back, and you can get either as part of an update or insertion, or when you get the key. And then if you want to make a conditional operation, such as an update or conditional removal, you have to press an e tag, and it will only be accepted if your version matches what is currently on the server. Also, you can do multi-key atomic operations. So if you have a batch of, let's say, 5 keys that you want to update at the same time, you can bash them together, and Pravega will ensure that they will either all go in or none of them will. And you can mix and match conditional and unconditional updates within this batch. So for instance, within those 5 updates, you can have 1 or 2 which are conditional and the other ones are unconditional, but the entire batch, the entire update is going to be conditional, those 2 ones. So you can be very creative with what you can do there. Of course, no key-value table will be useful if you cannot retrieve the data. So of course, you can go single and multi-key retrievals. And then you can also iterate through all the keys and all the entries. And currently in the code that we have out there in 0.8 and 0.9, you can group keys into key families. So one thing which I didn't mention is that key value tables, when you create them, you have to define a number of partitions. Each partition is pretty much a table segment. We do not yet have support for all scanning within key value tables, but that is something we are considering for the future. So right now, when you create this, you have to define a number of partitions up front. And in order to support those multi-key atomic operations, those keys have to essentially be mapped to the same table segment. In 0.8, I mean, which is what we have right now, the way you do this, we have a concept called the key family, and this is what we use for making sure those keys are hashed there. But I put a little star there because with the changes that we're planning to make in 0.10, we're actually gonna retire key families and replace them with something much more useful, and we'll talk about it in a few slides. So a quick summary of the history of key value tables. So we introduced them about 3 years ago in 0.5 when we first made table segments. Next release, we moved all of the segment store and controller metadata to use table segments. And then, so the goal of the initial table segments was to finally produce a public key value table. But we wanted to solve multiple things. That was one of them, but the other one is previously we used to have all of our metadata stored in Zookeeper or scattered throughout our tier 2. And we had various problems with scalability and frequent operations doing that. So we couldn't, so we had to figure out a way. And what better way of doing this than to dogfood it to ourselves. So first we made the table segments, and for 2 or 3 releases, we kept them internal to Pravega to make sure that everything works as planned, and that before we make it available to external users, it's stable and it actually meets the things that we are advocating it does. In 0.8, which was released in September of last year, we published beta 1 of key value tables, which is what we have right now out there. In 0.9, we have released SLTS, and SLTS, the entire chunk metadata is put on key value on internal table segments. You may have heard about a schema registry. The schema registry metadata is also stored in table segments. And now in 0.10, which is what I'm going to be talking in the next few slides, is the beta 2 of key value tables, which, as you're going to see, is a big improvement over this. Our goal is that soon after, maybe release 0.11 or 0.12, we're going to be having fully supported stable key value tables. All right, so let's go and see what this beta 2 is about. First of all, for beta 1, we have made various performance tests and longevity tests, and we figured out that there are a number of things that have to be changed, that aren't working properly. So we have actually found we've taken a different approach to key value tables, and we've made some major backend changes. I'll detail them in the next slide. The best thing about the beta 2 is now all the key value tables are sorted. So then we will provide order between keys, which will enable additional use cases to be implemented, such as range searches or prefix searches. There will be some minor API changes. Overall, the API stays more or less the same, but we are retiring key families. Why? We'll talk about it in a bit. And the keys are actually broken down into a primary key, which is required, and a secondary key, which is optional. Now, since we retired key families, we've replaced them with the primary key, which is your main thing, and we use that for affinity. Now, secondary keys, you don't have to use them. They're optional, and the reason we have two types of keys here is because not all use cases want to have multi-key atomic operations, but those ones who do want to do that, they have to, we can only do it for keys which share the same primary key, which is why we managed to do this breakdown. I have two examples coming up, and I'll explain how this can be used in practice. And for the APIs, now we are planning to support iterators for all the keys within the key value tables, courtesy of them being sorted. We're gonna have key ranges and prefixes. So as a structure, each key value table is a collection of table entries. A table entry is literally a key mapped to a value, and it has an e-tag-like version, like I said before. A key is a mandatory primary key and an optional secondary key, where the primary key is just for the partition or segment affinity. For example, let's say we have this simple thing where we have the P stands for primary, S stands for secondary. Suppose you have 3 primary keys where P1 has 2 secondary keys, P2 doesn't have anything, and P3 has one with no secondary key and one with 2 secondary keys. And we have 2 segments, table segment 1 and table segment 2. Now, if P1 hashes to segment 1, pretty much they're going to be mapped to table segment 1. And if P2 and P3 map to table segment 2, then then those other 4 entries will actually be mapped to those segments, and they're going to be recorded in there. So table segment 2 will be the one responsible with all operations for that one. So one thing I want to say is, see here, I use secondary key S1, both for P1 and for P3. Now, you can have the same one. Regard this thing as a namespace. So S1 can exist both in P1 and in P3. They are different keys because internally we put them together, and that's how we create the internal key. So they are different. So let me explain a little bit why we chose to follow this new structure. First of all, we have flexibility in how we encode data. Previously, key families were strings, and so based on feedback that we got from you guys, from our beta users, that is a bit too restrictive. Sometimes you want to you just include some random data that makes sense to you, and you have to go out of your way to include it into some string just for us behind the scenes to decode that into a byte buffer and just stash it back. So we've decided to simplify this. So now everything in the key value table is no longer parameterized. Everything is a byte buffer or a byte array, depending on what you want to do. So in that case, it puts the control in the hands of the user. The user can worry about the serialization. So we only have to worry about the actual data within it. So why is this? It's because it's easier to understand ordering between keys. So we've decided to remove the parameterization. So the parameterization is when you get like fancy Java types and you pass a serializer to us, and then we convert that to a bunch of bytes or bits. But if you think about it, numbers are usually encoded using 2's complement. Okay, well, they can be encoded like that, or they can be encoded in a different way. So how do you explain to the user what the ordering between keys is? In the backend, we're gonna order keys based on the lexicographic bitwise order. So that means if you see everything as a sequence of bits, it's pretty much like we compare zeros and ones and we put them in order. So in that case, it's easier for us to explain. If you give us a byte buffer, which is like a sequence of bits, then the order is going to be based on comparing the bit by bit. So it's bitwise lexicographic. And also, giving us byte buffers is easier for us to do prefix or range queries, because all you have to do is give us, okay, here's a sequence of bytes or bits, give me everything we start with this. While if you had parameterized data in with us, it would be hard to say, okay, well, how do you break down a 4-byte integer? What is a prefix for that? So we want to simplify it so we can actually give more power to the user. Let me give you 2 examples now. The first one is our textbook example, the one that usually you see in your university courses. Suppose you have a 2-dimensional table, a multi-column table. You have employee IDs or whatever you want to have in here, and you have columns, which is name, role, and whatever address. In this case, in our case, each row needs to have a unique identifier, and same with the column. We cannot have collisions in there. So how would you store this in a KeyValue table in Pravega? So you have 2 options. Let's look at row format. In the row format, your keys are made of a primary key and secondary key. If the primary key is your row ID and your secondary key is a column ID, then it's trivial how to encode this table in a sparse format. So if you look at the example on the left, in this way, it's very easy to say, okay, give me the entire row or give me a subset of the values within a row. So every row is stored atomically, and you can go and iterate to all the rows. But in some cases, you want to have a columnar format. In that case, we swap the order. So first you encode as column, and then you put the row IDs. This is pretty much like your favorite vertical format. So in this case, say, okay, I want to get all the values within a column. So give me all the names of the employees, or give me all the roles, or whatever addresses. You can imagine what kind of creative queries there. Of course, this is not the only way in which you can encode this kind of data. I'm just giving you one example. Developers are very creative, and so are you guys. So you just imagine the range of possibilities you can do here. However, Pravega is not really meant to be like a SQL replacement or no SQL replacement. Pravega is a streaming storage engine. So let's look at an example where we can marry streaming data with a KeyValue table. So in your typical pipeline, you have event producers. They produce events into an input stream. Then you have your favorite stream processor, whether it's your own homegrown one or whether it's Flink, where you put your stuff or whatever you want to do. And then from there, you may have the other downstream components, whether they are specific to your application or may have different stream processors. Well, that's your classical pipeline. But now, let's see if you can interject a KeyValue table in there, and then how can you use that thing? And again, let's start with the stream. Let's say that the simple stream is just somewhere to record events pertaining to some sensors. Our sensors measure temperature, pressure, and somewhere. I don't know, it's just some generic thing. And each event may have some sort of a timestamp in this example. So let's take this. So the red ones are sensor IDs. We prefix them with the type, which is a temperature. We have PSI and we have rate. And the number after the underscore is pretty much like some unique identifier for that sensor. So we have 2 temperature sensors, 2 pressure sensors, and 2 rate sensors. And they each produce some values, and the timestamps may not necessarily arrive in order because our favorite network delays and other time drifts, but they're also in there. So let's look at one thing. So first use case. Suppose that we want to get all the values for a sensor type or all the values for a sensor within a time range. In this case, our stream processor can maintain a KeyValue table, which is encoded as sensor ID and timestamp, which points to event values. So if our primary keys are the sensor IDs and the secondaries are timestamp. Remember that every key in a key value table now is going to be sorted. So it's very easy to say, okay, give me all the values for a sensor type, which means, okay, suppose I want to get everything for temp1 or for just for temp, and we can do a range search, so a prefix search, everything that starts with temp. In this case, we're going to get the first 3 entries, and you're going to get all the values. But suppose you have multiple values in there, say, okay, I want to get everything that happened for a particular sensor within a specific time range. So say for temp1, I want to say everything that happened between time range 500 and 1500. In that case, it's going to return a listing of entries, which is in our example, just the first one. So you can be clear there. Now, let's see what happens if you reverse the order of the keys. So first you make your timestamp as the primary key and the sensor ID as being your second one. Well, this turns a little bit into some sort of a time series database. I'm not advocating that this should be your go-to time series database because, you know, any key value store, any database can be a time series databases, but time series databases are a different domain of their own. I'm just giving an example of how this can work out. So if you use timestamp as a primary key, then look how your data is going to be ordered now. And that enables the different types of queries. So you can use your key value tables and say, get all the values within the time range. So I want to see everything that happened between time 1000 and let's say 1050. And you can do a quick range query, and you can get that. So why would you use a key value table versus just processing your stream? Well, if you process your stream, imagine this, you may have millions or even billions of events. In order to get any sort of query answer from your stream, if you don't have anywhere to index this data, then your only solution is to do a full scan of the stream and find your answer. Well, key value tables in this case enable you to do interactive queries. So you can, based on your specific application logic, you can say, okay, I'm going to process my stream and I'm going to remember some points which are of interest to me. So that later on, when I need to go access that data, I don't have to go waste my time to scan the entire stream, and I just have to remember those interesting things. So that's one way how we envision the key value tables could be used to complement your streaming environment. Okay, so I'm gonna spend one slide and I'm gonna talk about what is this big backend change that that enables all of these new things in beta 2. So we introduced something called a fixed length key sorted table. So overall, they're vastly simplified compared to existing table segment implementations, simply because we are able to insert the keys directly into our segment attributes. So we don't have to do any hashing or collisions in the backend. So most of the infrastructure that we have for table segments on top of regular segments have to do to resolve collisions and hashing, and that introduces some amount of complexity. However, if we can get a concession from the application that, hey, your keys are always the same length, and those lengths have to be like, let's say, less than 256 bytes, which covers pretty much all of the use cases I've seen so far, then we can offer you a much faster implementation, a simplified one with a smaller footprint and with fewer resources required in order to support your queries. Yes, you will have to be subject to some constraints, like all the primary keys and secondary keys have to be the same length, and your keys have to be less than 256 bytes to begin with. But as an added bonus, you get sorted key value tables, which you did not get before. So in our opinion, this was a worthy trade-off. I looked at the feedback that I got from various people that were trying out the key value tables in beta 1, and I saw pretty much virtual all the use cases can fit within these constraints without any problems. I'm hoping that these changes will not impact whoever was planning to use this in a negative way. I'm hoping that this, on the contrary, I'm hoping that this can actually make this more useful to people. So a little bit about comparison. Of course, we can both in beta 1 and beta 2, we can do insertions, removals, updates, conditionals, and multi-key atomics. Yes, we had to reduce the key lengths from 2 kilobytes to up to 256 bytes, but we are providing order between keys, so we are sorted, and now you can list keys. And as an extra bonus, you can do prefix and range queries with a disclaimer that we are not signing up for the last one for 010, but it may be done in 011 or in a subsequent release. But we are putting that on our roadmap. And if you want more info, we have a dedicated Slack channel in our public Slack. And we have links to the beta 1 design proposal, which includes a lot more technical details than what I was able to present now. And our latest and greatest just out of the oven, PDP-48, which describes the design and the architectural changes, and also the proposed API for beta 2. And you don't have to remember those links. Just go on the Pravega GitHub on the wiki, and we have all the PDPs listed there. Just look for KeyValue Tables or PDP-48. So that's it for me. This is the end of my presentation. I see there's a bunch of questions in the chat. So I'm going to open up for like 5 minutes of discussion before we go to Raul.
One of the features that we use a lot from Zookeeper is time to live Z nodes for things like leases. Would you see, so if we use the timestamp as the primary key, could we kind of simulate a time to live node by doing prefix searches and deleting based on the timestamps? Have you thought about kind of that time to live feature replacement?
So actually, that's one of the questions I see on the chat. It's question number 2. So that's actually a great one. So one thing with distributed systems and with distributed storage is that you have to be very careful what you mean by time. So if you leave time on the server side, you pretty much give us some control. So as of right now, we do not have a notion of time baked into our key value tables. So simply because we have the same thing even with streaming. So it's very hard to do anything with time which is actually reliable, which can meet most of the use cases. But if your application encodes time in your keys, like you said, then it could be possible to build a layer on top of the API that we build to implement the time to live support. So we can probably do that.
Yeah. And I think that also kind of relates to one of the other questions from Maxime, which is, range removals. Because if you were searching for a whole bunch of keys in order to manually delete them, then having that ability to delete from a range of primary keys would be really useful.
Yes, that could be done. However, you have to understand we do not have so as opposed from streams where you have distributed transactions, here we do not yet have support for distributed transactions. So that's one of the reasons why we have the restriction that all the multi-key operations have to be on the same primary key because they have to go on the same table segment. So if you want to do a range removal across multiple primary keys, that may actually end up being on multiple table segments. So we cannot guarantee atomicity. So that could be built as a layer within the client, but if the operation fails because something crashes on the client or somewhere else, the operation will only be partially executed. So we'll be up to the application to go and handle that, either a partial removal or just resume the operation.
What about within a primary key?
Within a primary key, so since that goes on the same table segment, that can be easily done. It's not in the API, but that can be done as a future enhancement. So let me answer question number 3. Are keys with non-fixed length still support? So the backend implementation exists. We have temporarily removed them for 010, and I'm only planning to add them if there is demand for them, because there will have to be a added back from the client. But they still exist in the backend, so we still have support. But for those ones, we cannot have them sorted. They will just be like your regular non-sorted hash table. So I'm asking for your feedback. If our users want this, then we are open to doing that post release 0.10. Count of a number of keys in the array. So you can do it by listing the keys. We do not keep statistics for keys within our data store yet.
Hi, Andre. I had two questions about listing. On the previous slide, the changes, instead of listing by key family, said listed by primary key. Is it required to include a primary key, or only if you're doing prefix? Like, can you just get an iterator for all the keys?
All right. So in Beta 2, we have essentially replaced key families with primary key, and we made it more flexible. So from that point of view, there shouldn't be much of a change in there. So you can list all the entries within the primary key. That's already coming in. But the next one, which is the last entry, the prefix range queries and global iterators, yes, we can support them. However, if you look at the footnote number 5, it's not within our scope of release 0.10. It is on our roadmap. We are going to try to do it in 0.10, but it may actually be done in a subsequent release. So yeah, it is in our roadmap, to answer your question.
Okay, yeah, because we're coming from the data's like opaque to us, right? Like, we might know the schema of everything, but we wouldn't know the primary keys.
So I'll tell you why that. So while listing by primary key is just a simple delegate to the table 7, which is already built there.
Oh, okay.
Globally, you have to do it distributedly across all the table segments and do a synchronous sort on the client. So that is a bit complex. We have to consider what could go wrong and whatever. So we want to take our time and don't rush it. That's the only reason why we are not signing up for it in 0.10.
Okay, gotcha. Okay, thank you.
So I'll take one more question because we want to get to Raul before we run out of time. All right, will increasing the number of partitions ever be supported? So maybe. I do have an idea how to do auto scaling, which could include the increased number of partitions. Maybe doing it manually is one way. But there are a number of complications and things that have to be handled there, and we did not sign up for. So we don't want to do it yet in beta, in the beta version. But that could be something which can be done if our user community wants it. All right. Well, cool. Well, thank you. Those are some very good questions. Thank you for listening to me, guys. I'm gonna post this PowerPoint presentation on KeyValue Table channel, which is right here in the open Slack. And with this, I'm gonna stop sharing and I'm gonna pass the buck over to Raul.
Yeah, thanks, Andre. Raul, you ready?
Yeah. 1 second, I'm going to share my screen. Yeah. Can you see my screen now?
Yep, I can.
Okay, perfect. Okay, so yeah, my name is Raul Gracia. I am a software engineer in the Pravega team for 3 years now. I'm going to, go over the performance of Pravega under parallel workloads, which has been one of the main focus of work for the 09 release. So this will be the outline of the presentation. We'll just briefly mention what's new in Pravega 09 in terms of performance. Then I will briefly go over the experimental setup for the experiments that we are going to see in the results section, and then I will just wrap up. So what has been new in Pravega 09 for the in terms of performance, right? So our goal has been to basically improve the data ingestion performance for those scenarios in which there is a high degree of parallelism, meaning that there are many writers, dozens, or and writing to thousands of segments, right? This could be a plausible scenario in edge or IoT workloads. So we targeted that one. You can see here a few of the main contributions. This is not an exhaustive list, but there are a few of them of the pull requests that greatly improve the performance of Pravega in those situations for those workloads. And basically what we achieved in Pravega 09 is that Pravega now has a better throughput when dealing with many writers and segments in parallel. It provides also a lower write latency, especially with working with connection pooling. Just for those that do not know what connection pooling is basically a feature in the Pravega writer that basically multiplexes the writes for multiple segments for a given segment store, right? So in this particular case, which really fits the kind of scenarios we are evaluating here, we had a very significant improvement in write latency. Also, Pravega is more stable under highly parallel workloads, and it consumes a lower amount of CPU. So all those achievements, we are going to go over the main results that we have in an evaluation we did doing experiments on Amazon. So I mean the full report, you can see that in the blog post that we published 1 month ago. But in this talk we are going to go over some and overview some of the results. So let's start with the experimental setup we used to do the performance comparison, right? So basically, in most of the experiments we have in that blog post, you will see that we basically fixed the incoming throughput, right? In this case to 250 megabytes per second using 1 kilobyte events, right? And what we change as knobs is the number of producers, or writers, and consumers as well, and the number of segments, right? So we fix the throughput and basically change the parallelism of the same workload to see the impact of that in the different systems, right? Another important point is that we used routing keys, basically chosen at random when writing data to the storage systems. And of course, we compare Pravega against the same workload for Kafka and Pulsar, right? In the table in the right side, you can see, in detail what are the main settings we used for this comparison. But a few of the main points we have to take into account is that we use the same replication scheme for all the systems, 3 replicas, and waiting for 2 acknowledgements per write. And also the kind of instances that we used, right? So we did the experiments on Amazon, so we used, in this to emulate this kind of highly parallel workloads, 10 VMs for running Open Messaging Benchmark, which is the tool that we use to execute our experiments, right? We had in all the cases 3 server instances, and in all cases as well, we use a single NVMe drive for journaling, right? So that being said, let's go over the results, right? We are going to focus on both throughput and latency. So let's start with throughput, right? So in this comparison, you can see, or in this plot, that Pravega can achieve the 250 megabytes per second, right? In basically, irrespective of the number of producers and number of segments, right? You can see the blue lines on top of the 250 megabytes per second target rate all the time. But this is not the case for Kafka, right? So what we observed is that there is a point as soon as we add more partitions to the Kafka producer, we see that the throughput rate that we can get goes lower. This can be mitigated by adding more producers, right? So you can see that for 100 producers, we get higher throughput compared to that with 10 producers, but still there is an upper bound to this improvement, right? And this is for the gray lines that you can see in Kafka, which is the default mode in which it does not flushes each write to the drive before acknowledging. We also compared, with Kafka when configured to flushing each and every message to the drive before acknowledging, which is the ping lines, right? So you can see there that adding this durability guarantee to Kafka really induces a very high penalty in terms of throughput, right? If we compare with Pulsar, one of the things that we observed with Pulsar is that with the configurations that we define for as a default for all those experiments, we got a very unstable behavior, right, from Pulsar. Actually, we observed that when writing with many writers and using many segments in parallel, using acknowledgement quorum 2 induced frequent out-of-memory on bookies, right? And this, couldn't, allow us to complete the full set of experiments that we are showing here. The other thing is that using routing keys, we observed also very often problems in, between bookies and Pulsar brokers. Basically, what we observed is an operation rejected error, right? That if you go, it boils down to be the DB ledger, which is the ledger that is configured by default in Pulsar. The DB ledger not being able to keep up with the amount of writes to the journal, right? So for this reason, you can see that Pulsar, which are the red lines in this plot, you can see that in this case, almost none of them could make it more than for 100 segments, right? So what we did to see what the problem was is to use a more favorable configuration for Pulsar, right? So instead of using acknowledgement quorum 2, we use acknowledgement quorum 3, right? So this basically reduced the amount of out-of-memory issues we observe in Pulsar, and also we configure the benchmark to do not use routing keys instead of using them at random, right? This ideally would improve the capacity of the client to batch writes and make a more efficient, writing to the server. This favorable configuration, you can see that in the yellow line. And for example, for the 10 producer case, we could get also the 250 megabytes per second in all the cases. But again, for the 100 producer case, we observe also crashes at 1,000 segments, right? So yes, we observe a much better behavior for Pulsar when changing those settings, but still is not fully stable, right? Which also has an implication, right? Because not using routing keys, the fact of that having an improvement means that, writing in parallel to all the partitions, it's a difficult scenario for Pulsar, right? And the other metric we are going to focus is latency. So if we compare that with the latency between Pravega and Kafka, we can see that Pravega provides a much better latency for the 95 percentile write latency compared to Kafka, right? So we can see that the difference goes, is increased as we add the number of partitions to Kafka. And in the case of Pravega, we can see that in almost all the cases, perhaps with the exception of the 100 producers and 5,000 segments, in all cases we can achieve a single-digit millisecond P95 write latency, right? Which is very interesting. And yeah, also to mention that the fact of adding durability in Kafka again shows a significant increase in terms of latency. With Pulsar, again, we have the issue of the instability when using the default configuration compared to the other systems. So if we compare the favorable configuration, we see that with 10 producers, Pulsar provides similar or even better P95 write latency compared to Pravega, right? But if we again go to the 100 producers case, we see that the write latency starts climbing until the system becomes instable and stops working, right? So yeah, that's the that's the summary of the results. And just as a wrap up, so we have done tons of work in Pravega Online to improve performance under parallel workloads. We also observed that Pravega provides better results than Kafka and Pulsar in most cases. And of course, if you want to see the full details on the comparison, the code we used, and all that set of details, please read the blog post. And of course, if you have any doubt, ask in the Slack channel. And yeah, stay tuned for new updates in performance. So yeah. You have any question?
Where do we go from here in terms of performance, or maybe even future evaluations? Do you have an idea of that?
Yeah, there are many open fronts here, right? So at least what we are evaluating now is the read performance, right? So we have been working on the write path for, I don't know, 1 year so far. But now what we are, being interested in improving is to evaluate the read path, because in some situations when dealing with, thousands of segments and very small events, we see that readers are not as efficient as writers. There are reasons for that, right? The kind of contract that the Pravega reader provides, but still we are trying to improve, especially the read side at this point, and there is work to do there. Of course, there are other things that are also very critical, including transactions, and yeah. So, and I am aware that, for example, Andre is also working on on the performance of the KeyValue store. So yeah. Many open fronts in that. So we are not going to get bored here. Yeah, if I don't know, any question? If not, yeah.
We have a few minutes. Are there?
All right, that's great.
Yeah.
Sounds like we were able to finish on time this time around.
Yeah, I think so.
Better.
A little early even. Any questions or comments on
Early
anything
even, yeah.
that was seen, or otherwise I'll just show my last slide.
Derek, I know we had talked about spinning up some Summer of Code and some other projects. I know this is out of the blue, but do you have any projects or initiatives that are kind of coming soon that people that are interested in collaborating could tag into, or things that people should be looking out for?
Well, I guess the most immediate
If we're not
thing
ready,
is
that's an acceptable answer, I should say, since
I think, well, I think that, I don't know if you can see my screen, but the hackathon, I think is the big thing. I don't think I can participate in the hackathon, but I'm excited to see what other people come up with. In just the first week of marketing, we're seeing some good traction here. They're seeing some numbers that are unique to us that aren't seen with other Angel Hack hackathons. So that was nice. But yeah, I would say just get involved in Pravega if this is up your alley, or
yeah.
Go ahead, Flavio.
Can I say one thing about that? So yes, let me say one thing about that. So if you're interested in contributing, I see at least two say obvious paths. Okay, so one is if you have, say, a processing engine that you want to connect to Pravega, right? For example, the Akka work that Olivier presented in the beginning. So if you have a system like that, you're interested in using Pravega, then working with us on building a connector, that would be a way. But if instead you're looking to contributing to Pravega itself, then at this point, I don't think we have a very clear way of communicating this. the best way would be to reach out on the Slack channel and perhaps interact a bit with us, and then figure out what would be a good way of starting it.
Yeah, so I was just going to close, I guess, with that. The Slack invite is pravega-slack-invite@heroku.herokuapp.com. That'll get you access to the Pravega-IO Slack workspace. So, yeah, join us there, and maybe join the discussion about what happens in Zero10 and or what you'd like to see in KeyValue tables. Check out the blog, like Raul said, his performance blogs are there on the blog, and there's a new one about Pravega Sensor Collector, which is really interesting. That one works on Windows with WSL2. Our next May 21st meeting will be Flink, GStreamer, and Presto, and that event is up on the community site. And then, of course, if there's any feedback, email me at derek.moore@dell.com. So yeah, thank you, everybody. Those presentations were really informative for me. I'm sure they were for everybody else. I was really amazed by the Akka stuff. It was, I didn't expect the KeyValue Table integration to be so seamless, but I thought he really showed the value in his simple demo.
Oh, Flavio, is it just my audio? I couldn't hear.
Yeah, sorry. I was saying that it's interesting you mentioned it, because when I saw his diagram, I was puzzled because he was showing a table and it has the Pravega feature, and I didn't realize he was using KeyValue tables. So what the heck is going on there? But then say, yeah, I'm using KeyValue tables. So, wow, that's cool. Yeah. Well, so yeah, I really like the presentations today, and thanks everyone for joining. So next one will be pretty good too. So hope everyone joins next meeting as well. Thanks, Derek, for pulling this up.
Yeah, you're welcome. Yeah, the 3 connectors next time should be pretty powerful. So, all right, I guess I'll end the meeting. Take care, everybody.
Thank you, guys.
Thank you.
Thank
Bye.
you. Bye.
Everyone.